This is Professor Pelton. This is Algebra 2, Chapter 6, Section 2, the natural base E. E is the Euler's number, discovered by Leonard Euler in Europe in the 1700s. It's the natural base. It's known as the italic E. The three italic letters you should know from high school are E, I, and pi. E and pi being very similar, they're irrational numbers. These basically keep going on forever and ever. E is used in financial formulas and amongst other things where we see compound interest, it's being used. So it's calculated several different ways. The way we're going to calculate it is the limit of 1 plus 1 over n to the n power. We just keep replacing n with larger and larger numbers until n gets to infinity. Then you have the true value of e, which of course goes on infinitely, hence why you want n to go to infinity. And you're getting close. So this is an approximate value of e right here out to the specified number of decimal places, which you can count for yourself. You can get more by increasing the value of n. So do an example in the calculator of what e value looks like. So it's parentheses of 1 plus, we'll do a fraction of 1 over 10 to the first power, all to the power of 10 to the first power. So that gives us a 2.5, and the value of pi e is really 2.7. So that's only good to one place value. So I go up and copy this, Control C, Control V, and we'll change this to a 2, and we'll change this to a 2. That gives us 2.70 when the actual value of e is 2.71. So that's correct to two place values. We'll do this again. We'll paste it, but now we'll put a 3. This gives us 2.716 when the actual value of e is 2.718. So this is only correct to approximately 3 place values. You can see the pattern as it goes on. Okay, so go back to the other page. So do you have to do it in powers of 10? No, but this gives you a nice little pattern as far as how accurate you want to calculate it to. Your calculator also has an E button typically on it. So this is approximately 2.5, but that's not correct. It keeps going, obviously. This is 2.7, and it keeps going, but those numbers afterwards are not correct. 2.71, those numbers are not correct. 2.718, not correct. After that, 2.7182, not correct after that. 2.71828, and not correct after that. Obviously, just go to infinity because it's a limit, which means go to the limit, right? So that's how you get the value of e, which is now we're going to graphically compare e to what we did in prior chapters or prior sections rather. Okay, so we have 2 to the x, 3 to the x, and I'll do e to the x in between. Let's see, why is that? Well, the value of e is 2.71 and some change, which is higher than 2, but lower than 3. Okay, so we'll do a table of values for all of these. Okay, so for these ones, you can do nice whole numbers, and we can figure them out for ourselves. Okay, so 2 to the negative 2 is 1/4. I get 1/2, 1, 2, and 4. Okay, so at negative 2, I'm at a quarter, then I'm at a half, then I'm at 1, then I'm at 2, then I'm at 1, 2, 3, 4. We can do one more, and 3 is at 8. 2 to the third is 8. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8. So that's approximately right about like that. Okay, and we'll choose a different color. We'll go with a red perhaps for this one. So that's 3 to the negative 2, which is 1/9. That's 1/3. That's 1. That's 3. That's 9. So at negative 2, I'm at a 9th. So that's pretty small. Then I'm at a third. Then I'm at 1. Then I'm at 3. then I'm at 9. So you can see it's below over here. Then it crosses at the 1, and all of a sudden it's more. Okay? Either way, you can't get to 0, right? So we have an asymptote at y equals 0. Well, here's the thing with e. If I do -2, -1, 0, 1, 2, I can't do this in my head because e is an irrational number like pi. I can do e to the 0, that's 1, because anything to the 0 power is 1. So this is 1 over e to the second power. I have to use my calculator, okay, and get those values. And when I do those values, what am I going to get? I'm going to get approximately 0.135, 0.368, 1, 2.7, and 7.4. Okay, so what happens is I end up being between these two. Another different color here. We'll go with the green. I end up being between these two, still crossing at the 1, and we're between again. Because at 2, we're at 7.4. 1, 2, 3, 4, 5, 6, 7.4. We're about right there. Okay. So it's just between them. So is there any difference between 2, 3, and E? No, don't overthink this. It's the same graphs as the previous section. My domain is still anything I can plug in for X is fine. There's positive, negative, and 0 for X. However, no matter what I plug in for X, I can't get 0 and I can't get a negative number. So it's 0 to infinity for my range. Okay, so in general, the natural base is very similar to what we did in section 1. Except when you distinguish between growth and decay, you have to look at the rate or the R value that's being put in the exponent, okay? If that value is positive, you have growth. If it's negative, you have decay. You notice the graphs look exactly the same. As you read left to right, you have growth. As you read left to right, you have decay. And it all comes down to the exponent, is it positive or negative? Okay, let's do some examples on the next page. So again, you're not going to be able to do these if you want exact or nice values. It's not going to happen. You have to, so when you do tables of values, you're going to need a calculator because E is irrational. Okay, it goes on forever. So if I did a table like this, the only one I can do effectively is the 0 because that is 3e to the 0, and the 0 power is 1, so I get 3. The rest of these will all be decimal values. So if I use my calculator, I get 0.41, 1.10, 8.15, and 22.17. Okay, so at 0, I'm at 3. At -1, I'm at 1.10, 0.41, 2, 3, 4, 5, 6, 7, 8.15. The other one's off the graph, which is okay. The reality is, looking at this left to right, it's clearly exponential growth. And you should be able to tell because x is just a positive. There's no negative in front of it because it's a 1x. The 1 is positive. Okay? So all you really needed to do was the 0. You could have skipped the other ones and made that graph, just make a nice little sketch of it because you know if you plug in 0, you get 3. Same thing here. If I make an x and y table, what's the only one I really need? I can do more of them if I want to. I only really need to use 0 because e to the negative 0.5 of 0 is e to the 0, which is just 1. So, and is this going to be growth or decay? Well, this is negative, correct? So that's going to be exponential decay because negative 0.5x, you have a negative coefficient in front. The first one's a positive one, this one's a negative 0.5, thus it's a decay. So if you used your calculator and plugged in the values, you did, e to the negative 0.5 times -2, and then -1, you would get 2.72, 1.65, 0.61, or 0.37. Okay, so I'll put those on here. 1.65, 2.72, 0.61, 0.37. We got our approximate graph. And in both of these cases, we have an asymptote of y equals 0, because you're not going to be able to cross that invisible line because it's as an asymptotic function. All right, pause the video, try the student problems. Okay, without doing any work whatsoever, this one is exponential growth, and this one is exponential decay. Because if I look at these, this is a 1x, the coefficient is positive. This one is negative 1x, right? So it's a negative coefficient. Just looking at what I have up here for exponents. Okay, get the marker off that. So again, you can do a table of values if you want to, but the only one that's really necessary is 0, because if I plug in 0, I get 1/2 e to the 0, or 1/2 times 1, or just simply 1/2. Okay, and it's going to go up like so. You can do the other values if you want, -2, -1, 1, 2. You can do 3 and 4 if you want to. You'll get 0.067, 0.18 approximately in each one of these cases, 1.36, and 3.7. All are approximate because E is, of course, irrational. You're not going to get an exact value for those. And do the same thing here. Do an XY table. The only one you really need is 0. So if I plug in 0, it's 4 times e to the -0, which is 4e to the 0, or simply 4 times 1 for 4. So 1, 2, 3, 4. You'll get one that's approximately like this. I kind of missed the point there, but you get the idea. My markers. So if you do the other ones, you get 29.6, 10.9, 1.47, and 0.54. Okay, which doesn't need to be completely exact. Obviously, the 29 is not going to be on there. Okay, that is the end of part 1.